Okay. So now, now today's lecture, I do definitely want. I mean, this is something that I always say, but I want all of you to please speak up because it's going to be uh, interactive. The last couple of lectures, I've been doing a lot of talking, and so I just want to get some kind of a two-way interaction going in today's lecture. So let's see how much we can take it. Okay. So the idea in this lecture is, now that you have a kind of an overall background of groundwater modeling as a, I mean, sorry, groundwater hydrology as a whole, we are going to try and spend some time in trying to um, learn a little bit about how to model these systems in a more systematic way. So that is going to be the objective of this final module that we have. We will probably cover it in 3 to 4 lectures maybe, and then we'll have a couple more, one lecture to kind of wind up, and then we have the final presentation. I still haven't heard back on what the date for the final presentation is going to be. Uh, we need to discuss that as well. Anyway, okay. So when we talk about groundwater modeling or modeling in general, the next question that immediately begins to come to our mind is, what is a model? Because groundwater we understand. Now I have thrown this new word in there, modeling. Okay, so what is a model? Anybody would like to volunteer and kind of throw some ideas? What is a model? Anybody? What do we understand by a model? Forget about groundwater modeling and all of that. Generally speaking, if I say a model, what do we mean by the term model? If nobody volunteers, then I'll just call out somebody. So we'll go around the class. Okay. All right. Vicky, you can please unmute yourself. Yeah,
Yes, sir. Model is a small prototype.
it's a small prototype. Okay, agree with you. Thank you, Vicky. Manish, you can go back to mute. Yeah, thank you. Manish.
Yes, sir.
Yeah. So Vicky says a model is a small prototype. Do you agree with him? Do you want to add to that?
Yes, sir. Model is uh, either either big or small because like
Mhm.
model is similar to like a prototype or model analysis.
Okay. Okay. So you're kind of agreeing with Vicky. Ah, all right. Okay. Thank you. Hemant, do you have anything to add to what Manish and Vicky have said so far? What is a model? Okay. You're still on mute. Okay. Gautam or Shekhar, what is a model? Okay. I'll come to you, Yash. Wait. Oh. Purnima, what is a model? Alina,
So it's like a physical representation of something, like some
hmm.
kind of imitation, so that we can't do it on a large scale. We can't do it. So on a small scale, we are presenting
Okay.
itself as a model or
Okay. Good ideas. Good ideas. Yeah. Thank you. Okay, Yash, what is a model? You raised your hand in between. Can't hear you. I don't know if others can hear you, but I can't hear you. I hear some. Air. Maybe you can put in a chat.
Hello. Now is it okay?
Yeah. Go ahead, Yash.
The model is any kind of representation, might be physical, might be not, but we should be able to learn from it, make improvements on it, like for what the model has been made.
Okay.
On that aspect, we should be able to make improvements on it. We should be able to properly represent what
Okay.
what
Okay.
that model is meant for.
Okay. Thank you. Yeah, Deepshika, you just joined just now. Just to give you context, so we are going to be spending the next 3 or 4 lectures on groundwater modeling. I'm going to give a brief introduction to groundwater modeling as a whole. Okay, so in that context, I'm asking the question, what is a model? Okay, so groundwater modeling is specific. Now I'm asking a general question. In general, what is a model? Deepshika, any thoughts? Some people said it's a prototype or a representation or a small scale version, something like that. Any additional thoughts that you have, Deepshika? Okay. Gautam, you left and came back. Would you like to maybe unmute yourself and try now? If you have something to add. Okay. Looks like. All right. Anyway, fine. No problem. Go ahead.
Hello.
Yeah, go ahead.
Yes, sir.
What is a model?
Sir, it is like a 3-dimensional space that we can set bound. They can define by boundary conditions basically.
Okay.
We can have boundary conditions to limit the space, and
okay.
We can have input to the system and get output from it.
Okay.
So
okay.
we can define a function which defines the 3-dimensional space in it.
Very good. I agree with everything that you said. But it need not be 3-dimensional. You are saying 3-dimensional is one.
Yeah, sorry. Means not only. Yes, correct.
Yeah.
It may be 2-dimensional.
It could be 3-dimensional.
Yes.
It could even be 1-dimensional.
Yes.
Okay. 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 So basically, I think everybody is on the right track. You have an idea of what it means to, what it means when you say a model. Okay. Thank you, Gautam. You can unmute yourself. Yeah. Thank you. Okay. So basically, a model is a representation of reality, right? That is the real world. Right? You might have seen, you know, if you go to some shops, you will have available a small ball which has got all the continents and the countries and the oceans and all of that, a globe basically. Is that a model? Yes, that is a model. That's not the real world, but it is a representation of what the real Earth looks like, right? The different continents are shown, the different oceans are shown, the different countries are shown, and so on and so forth, right? So it could be anything. It could be a map, it could be a photo also, right? If I take a picture now, okay, what you're seeing on screen, if you're seeing my picture, my video or whatever, that's not me. What you're seeing is just a moving image of me, right? I mean, okay, maybe I could even add video to that. It's not just a map or a photo, it could also be a video. Because what you're seeing is just an image of me. It's not me actually, right? It's a virtual image of me, okay, sitting all the way in Canada, but you're seeing that as if I'm sitting there in person in front of you, right? So that could be a map or a photo is a representation of reality. Like, for example, if I draw on a piece of paper the India map, that's not India, right? That is the boundary of where India is on the global map. And as soon as I draw it on a piece of paper, you know what I'm doing, right? Even if I draw it upside down, you know that, okay, I just have to turn it upside down, and this is north, that is south, this is east, this is west, and all of that is north, right? It could also be a miniature representation, like some of you said. If you're going to construct a big building, right? Especially if you're going to buy a house or something like that, if you go to the real estate person's office, they'll have a small replica of that building just to show you what it will look like, right? They may even give you a 3D tour of that, or a virtual tour, right? That's through a model of what the house is going to look like, right? So it could also be an idea or a conceptual model of your, okay, I think that this is what is happening in this particular reality, right? The river is connected to the aquifer, let's say. Okay, that is your idea of it. You have not gone and seen the connection, right? But you have a conceptual idea that the aquifer is connected to the river, or it's connected to this or that, whatever it is. So all of that could be a model. Finally, I've listed a mathematical model. Now, when I'm talking about groundwater modeling, what we are typically referring to is a mathematical representation of reality, right? I'm using some equations to try and predict what the water level is going to be at different points in space, right? Using some mathematical equations. So basically, it is a mathematical model using which we are trying to represent the reality, right? In this mathematical model, we might need additional pieces of information, right? To indicate that this mathematical model is for this particular region, right? It is for this particular soil type. It is for this particular rainfall amount, or it is for this particular depth of soil, and so on. Right? Those are other factors, right? For which you may need additional models, like a picture of the location, the boundary of the location, the watershed boundary or the administrative boundary, and so on and so forth. So basically, a model is some kind of a representation of this reality. Okay, that's what we are trying to say. Now, in the context of groundwater model, I'm going to classify it into a few different basic types of groundwater models, right? So you could have a physical model, which is what is called a sandbox model, right? I take a box, fill it with sand, okay, and pour some water into it. That is also a representation of how groundwater behaves, right? So what I can do is, I have a real aquifer in the real world. To mimic that, I take maybe a glass box, or a plastic box through clear plastic, and then I pour some sand into it, or pour some different types of soil into it and compact it, and then pour some water into it. Now that box is representing my real world aquifer, right? So it's a physical model. It's a physical actual sandbox, okay? Or it could be a conceptual model where you're thinking, it's an idea in your head, right? You are conceiving that, okay, so this is the different, these are the different layers in that particular aquifer. So that's a conceptual model, right? It's a concept. You may also have an analog model, right? Now, I'll not spend too much time on this, but basically, if you think about it, our fundamental equation, Darcy's law, looks like this: Q equal to minus Ki, right? Now, in electricity, we have a similar equation, right? V equal to IR or whatever, right? Very similar to Ohm's law. Okay, these two equations, if you look at them, they look about the same. Of course, one difference is that in this equation, V equal to IR, V is the potential difference, which is the equivalent of the small I, that head gradient in our Darcy's law. R is the equivalent of K, and I is the current flow in the case of capital I is the current flow in the case of electricity, and Q is the groundwater flow in the case of Darcy's law. So it's not exactly the same, but you can see that there is some similarity between these two equations. So what you can do is you can use a circuit as an analog for the aquifer. You can say, I have a circuit with different resistors. The resistor of the model is kind of an analog to represent the conductivity of the soil, right? So if I have different types of soil and water is flowing through it, I can have different types of resistors and the current is flowing through it, right? So some kind of an analog. So people have tried to use these kinds of an electrical circuit as a representation of an aquifer. Okay, beyond the scope of our discussion here, and I'm also not very well aware about it, so I'll just leave it at that. So that's some kind of an analog. And then we have, like we discussed before, a numerical or a mathematical model. There could also be an analytical model, right? If you remember, we wrote a lot of different equations early on. We said dou square h by dou x square equal to minus r by t, right? Remember, we wrote an equation like this. Now, this is an analytical expression, which is telling me what the head will be in a particular, this is actually for a confined aquifer at steady state with recharge, right? It's a one-dimensional confined aquifer at steady state and it's a homogeneous aquifer because the T has come out of that equation. Anyway, so this equation you can solve it if I give you two boundary conditions, you can solve this equation, right? So now this is an analytical expression. So the difference between the analytical model and the numerical model is a little bit subtle. Okay, the analytical model requires nice, clean geometries, right? I cannot have an irregularly shaped boundary. So when I solve this equation, I'll say at x equal to 0, this is the boundary condition, and at x equal to L, this is the boundary condition. Okay, I cannot have some kind of an irregularly shaped domain, right? Okay, you can't imagine it in 1 dimension, but in 2 dimensions, the analytical model, suppose I were to write an analytical model in a 2-dimensional domain, it has to be a perfect rectangle or a perfect square, something like that. Only then I can solve the analytical model, because it requires boundary conditions at all these boundaries, right? But a numerical model, I can solve it even for a domain that's like this. It doesn't have to be a perfect geometry, right? So this is analytical model requires this kind of a domain. A numerical model can be solved for any domain of any shape. Of course, it can solve a rectangular domain also, but it can solve any shape basically, right? So that is the advantage of the numerical method over the analytical method. Analytical models are only applicable for perfect geometries, for homogeneous aquifers, and so on and so forth. Numerical model is also solving the same equation, but instead of solving it for this kind of a perfect geometry, it is solving it for an irregular geometry also. That's the only difference between the numerical model and the analytical model. Now, the advantage of the geometry is that using the geometry, you can get a closed form solution. You can just write the answer in a piece of paper. But if the geometry is complicated, like I've drawn here, you cannot give a expression which gives the answer h as a function of x and y. That's not possible in an irregularly shaped domain. In a regularly shaped domain, you can totally use this kind of simplifications and get an answer. Okay, anyway, so that's the distinction between numerical and analytical model. Okay, now we have gotten into the idea of what a model is and so on, but there is an even more fundamental question that we can ask even before we get into that. Why do we need to model? Okay, anybody has any answers on this? Why should we model? What is so great? Why should we model? Anybody? What is the need to even develop a model? Anybody would like to? Please. I don't want to call out anybody. Just anybody unmute yourself and just speak. Okay, is there to do analysis? Okay, so why do we need to model? One of the answers is to do analysis. Okay, it'll be better if you just speak up so that because then I can ask a follow-up question. What kind of analysis? I don't disagree with you. I agree with you. We need to model in order to do some analysis. Otherwise, who cares about modeling? What kind of analysis? That is the question that I have.
Maybe in reality, like we can't study all the things, like not economical or maybe complex, and also to solve it, make it easier to like instead of doing many of the experiment and study, to do it like in a model and representation kind of thing.
Perfect. Good answer. So what you're saying is that if I want to let's say find out what will happen if I do this, if I do that, if I try different combinations, if I try different scenarios, I can't test them out in the real world. Instead of that, I will have a model in which I try these different options and then see what happens, and then that becomes the basis for me to take a decision. Suppose I want to take the decision, what will happen if I pump so much water? I can't actually go in the world and pump out that water and then go and measure the impact. Instead of that, I run the model, and the model will tell me what will happen if I do this, if I do that, and so on. So that's a perfectly valid answer. Now, inherent in that answer, there is one assumption in there. Okay, in that answer, there is an assumption about time. When I say time, I mean, what I mean is about that. What Deepshika was trying to say is that I want to predict the future, right? So what will happen if this happens, if that happens? If I change the pumping, what will happen in the future? If I reduce the pumping, if I increase the pumping, if I increase the number of wells, if I increase the depth of the well, and so on, what will happen in the future? That was kind of implicit. She didn't say it, but I am adding it on her behalf. Okay, that we want to predict the future based on, let us say, what will happen if tomorrow I have so much rainfall, right? For example, now maybe it's more easy to think of it if I give you examples of rainfall and flooding. Okay, so let us say I'm in charge of a particular city, and the weather office, the weather department is predicting that in the next 5 days we will receive 20 centimeters of rainfall. Okay, so then I can say, based on the current scenario, if 20 centimeters of rainfall comes in the next 5 days or 4 days, whatever it is, what is the likelihood of flooding in the different parts of my city? I can predict that. Okay, now the weather department will also say it may be 20 centimeters, or it may be 18 centimeters, or it may be 22 centimeters. I don't know. Somewhere between 18 and 22, average is 20, right? So I can predict for 18, 19, 20, 21, 22, whatever it is. I can predict how much flooding will happen in my city. And based on that, I can take a decision. Okay, these people might get affected by flooding. Let us move them from this area to a safer area. Or in these regions, I may see some excessive flooding. So I have to install some pumps there to pump out the water. Or I have to decide my dam is already full. Okay, let us open the water and let out some water from the dam, so that when the new rainfall comes, I can store that excess water that is produced. So I can take decisions based on what is going to happen in the future, based on so many different scenarios that I'm looking at. You can extend this to groundwater also. Like I gave you the example, what will happen if I pump so much water? What will happen if I increase the number of wells? What will happen if I reduce the pumping rate? Whatever. So you can try so many different combinations. So that basically the idea is that I want to manage my water resources. Okay, as simple as that. Okay, and in that I'm saying I want to predict the future. So now, instead of calling it prediction, I'm going to use a fancier word. I'll call it forecasting. Right? I want to forecast. I want to know what will happen in the future due to certain behavior change, or due to certain climate change, or due to any other response, right? Even I can even predict how much recharge will happen in the future if I change the land use in this particular region. I'm going to change the land use. This place is previously rural area, now it has become an urban area. So what will happen to the recharge? And if that recharge happens, how will the water levels be affected, and so on and so forth, right? So that is forecasting in the future. Now, in the case of groundwater, there is also another application that I can use the groundwater model for. Why I can model, which is called hindcasting, right? Which you can say it is to understand the past. Okay, so this management of water resources itself has two kinds of applications. One is to forecast, which is to predict the future. The other is to hindcast, which is to understand the past. Okay, now why would you want to understand the past, or in what context would you like to understand or have to understand the past? Anybody has any thoughts? There are no correct answers. There are just different opinions. I would like to hear your opinions. Okay, don't worry about why would you be interested in knowing the past. Now, remember, I'm talking in specific about groundwater modeling. Okay, In groundwater modeling, why will I want to understand what has happened in the past? Anybody? What could be a likely reason for me to understand, for me to want to understand the past? Anybody has any thoughts, please? Come on, guys. Okay, if you're feeling shy to speak up, then you can even type. No problem. Quickly. I'll give you a clue. Okay. Let us say that today I found some contamination in my well. Okay. I have been using my groundwater well for the last 15, 20, 30 years, whatever it is. Same well, same location. Everything is the same. Okay. Suddenly, the last 4-5 days, let's say, or 1 week, whatever it is, I started noticing that there was some contaminant that was coming along with the water, and it smells like some kind of an organic material, right? It could be petrol, it could be something, whatever. So now, based on this, what is the role of this hindcasting or understanding the past? Does it have any role? Anybody has any thoughts? Given you a clue.
Yes, sir.
Go ahead, Shantanu.
There may be crude oil present inside the beneath of the rock or soil.
Okay, I'll add one thing. Now, it is highly unlikely that human beings are tapping into water sources that are so deep that you can actually find crude oil. Okay, so generally speaking, crude oil is found at much greater depths, because to generate that petroleum or crude, whatever it is, you need a lot of pressure and millions of years, right? So it's really deep. You will not find crude oil at close to the land surface. Okay, let us say it's not even crude oil. Let us say it is petrol. If it was crude oil, then it is a natural source, right? If I find petrol comes from this fractional distillation of crude oil, right? You must have heard about this fractional distillation. At different levels, you will get different liquids of different densities, right? So anyway, so suppose I find petrol in my mixed with my groundwater. It can't be from a natural circumstances. You'll only find crude oil. So why would I want to understand the past when I find petrol in my water today in the groundwater?
Yes, sir. Another aspect is our leachate, which is mixing with the groundwater, like contaminated ground, and then contaminated the groundwater, and this
Okay.
is by what is this carcinogenic compound is created in the water.
Okay. Now the question is, what is the role of hindcasting, or basically understanding the past when I see a contaminant in my water today? What is the role of hindcasting? Okay, so suppose I find something in my water today. I would like to know who polluted the water, right? When I say I, let us say I am the city of Tirupati. Okay, the municipal corporation of Tirupati finds some contaminant in its water, and it's not naturally occurring. It is some industrial contamination has resulted in polluting the aquifer, which provides water supply for the city of Tirupati, which has got whatever lakhs of people, right? So then I need to identify who contaminated the water so that we can take action and try to fix the issue. What if that pollution is still not stopped? If they are continuing to do something which is getting into the water, we should at least make them stop to prevent further contamination, number one. And then for whatever contamination they've done so far, they should be held responsible for it, right? Now, for me to predict where that contaminant came from, I have to know what happened in the past. So I'll have to, let's say, for example, I develop a groundwater model for that particular region, and then I have to track the water backwards from my well and find out where it came from, right? So I'll have to, let us say, what is called particle tracking. Okay, so I can do some kind of reverse particle tracking. Okay, basically release a particle and then track it backwards in time, okay, to identify source of contamination. So this is also an aspect of, managing my water resources, right? Because number one, that source of contamination may still have not stopped. Today I found it in my water. The pollution may have been happening for 10 years, 15 years, and maybe it has not even stopped. And unless we point out that there is this problem, see, my water is getting contaminated, please stop your contamination. Even future contamination cannot be stopped. Yeah, go ahead, Shantanu.
Sir, that means we have to find out the source, receptor, and the transporting agent.
Correct.
So to
The
find
transporting agent is water. Groundwater is the transporting agent. We need to find out the source of contamination, from where I am the receiver. I have received it and it has come along with the water. I need to know from where it came. There may be so many people upstream of me. There may be multiple industries. One of them or a combination of them has resulted in contaminating my particular well. So it becomes necessary to identify the source of contamination. So anyway, so that could be why I want to hindcast. The other reason could be, suppose I want to predict the future. Okay, how do I know that my model is good enough to predict the future? One typical way we do is, we have data from the past. What was the water level in 1985? What was the water level in 2010? What was the water level in 2015, and so on, right? Suppose,
yes, sir, by masker method, we feed in the masker, then predict for the future by the past data.
Yeah. So basically, I create a model. If my model is capable of predicting what happened in the past, because I have data from the past, right? So I can use that data in order to match it with my model prediction, and that will help me say that this model is good, right? It is able to match the past data. So therefore, I can trust this model to predict the future data, right? So it's a process of what is called model calibration / validation. So you can use it to, because remember, in my model, I will use different parameters: hydraulic conductivity, storage coefficient, recharge. All of these things are there, and I don't know the hydraulic conductivity at every point in the model, in the modeling domain, right? Or I don't know how much recharge is happening at every particular point. So I'm just putting in some value of recharge. Maybe that value is not correct. So in order to correct it, I have to predict the head at different points in time in the past and use the past data to tell me whether my model is predicting it correctly or not, right? And then accordingly, I have to fix my model parameters. So that process is called model calibration, in order to constrain the model and say, give me reasonable predictions. And once I'm convinced that the model is able to predict whatever has happened in the past, then I can say this model is good. It can be used to predict the future, right? So therefore, this hindcasting or understanding the past is very important. Okay, there is a third aspect of why we need to model, and that is, I'm going to just write that and then I'll spend a few minutes trying to explain that. Prioritize data collection. Correct? Now, before I build the model, right? I have to have some understanding of what is the behavior in this particular region, how much data do I have from the past, which I can use to build the model, right? The model, you can't just go to a shop and say, give me a groundwater model. Nobody has it. You have to build the model. And what do you build the model with? You build it based on existing data. You may have some information from different maps that are available showing how the land surface varies, right? How much rainfall has been received in the past, and so on and so forth. Soil type data, all of this data is available. And then you collect all that data and use that to build a model. Okay. But only when you build the model and then do this model calibration, you find that, you know what, my model is not able to predict the past information. No matter what I try, my model is just not able to do it. Okay, my model is failing. So then you realize that your model may be missing some very important information that is not available. So then you say, okay, let us go out and collect data in this particular region in this model, because my model is performing poorly in this region. Everywhere else, my model is doing reasonably well. But in one major area, my model is not able to predict anything. My model is saying something and something else is happening based on the data that was available, right? So then you go back and say, let us collect some more data. And then once the data becomes available, I may be able to correct my model. I may be able to say, hey, I assume that in this region, the soil was sandy, but it looks like it's not sandy. I went and collected data and found that the soil was clayey. Or I assumed that in this region, the thickness of the aquifer was 100 feet. But when I went there, I found that the thickness of the aquifer was only 50 feet, or it was 200 feet, whatever it is, right? So that information about what is happening in the real world, sometimes the model is also able to help us to prioritize, hey, go and collect data there. Collect this type of data, collect this much data, collect this quality of data, and so on. I might have poor quality data to begin with, and I built a model, but my model is not useful. Then I have to go back and say, I need to understand this particular area even better. So I need better data, I need more data, I need better quality data. And all of this can be done by building a model, right? You can use the model to prioritize future data collection in order to build the better model, right? My model itself tells me how to make it better, because the model is not able to predict the past information. It is telling me indirectly that I don't understand this particular region. That's why I'm not able to predict it. Give me better information, I'll be able to do a better job. That's what the model is saying to you indirectly, right? So you can use the model to prioritize data collection, right? So these are the different, I've just given you a few basic ideas of why we need to model. Number one, to predict the future, which is called forecasting. Number two, to understand the past, which is hindcasting. And I've given you different reasons why we want to understand the past. And number three, to prioritize my data collection, right? To understand the site better, I have to collect additional data, and sometimes that can happen through the modeling process itself. Okay, so that is general overview of why we need to model. Okay, now in our context, we are going to talk about numerical models alone or mathematical models alone. Broadly speaking, I mean, I'm just going to limit it to two broad types of numerical models. There are other types available, but I will restrict myself to these two broad types of numerical models. One is called a finite difference numerical model, and the other is called a finite volume numerical model, right? Now, the distinction between the two, there are many distinctions. Okay, one kind of more obvious difference that is most often given is like this. Okay, let us say this is my area of interest, this is my domain. Okay, when I use a finite difference model, I break it up into different grids. Okay, something like this. So finite difference model means I'm just breaking it up into more or less approximately square boxes. Of course, it need not necessarily be perfectly a square, but in general, this is what a finite difference model looks like, right? So I'm breaking it up into more or less rectangular rectangular smaller boxes. This process is called discretization. Discretization. Okay, why do you think it's called that? Because I'm breaking up this domain into discrete boxes. And what is my final objective? My final objective is to predict inside each box. I'll just draw some random box. This box, I want to know what is the hydraulic head. What is the head in that particular box? So in each box, I will have one prediction. What is the head? Once I know the head, I can use I can use Darcy's law to predict what will the flow direction be. Right? Because I know the head in each cell, I know the gradient, and once I know the gradient, I can find and I know the hydraulic conductivity. I can tell me what is the direction of flow, how much is flowing from that cell to the next neighboring cell, and so on and so forth, right? So the first step is, once I have a domain, is to discretize it and break it up into these smaller boxes. And at the end, I'm going to finally have a prediction for each box. Each box will have a final prediction. Now, in a finite volume, again, I will try to restrict myself to a very simple way of defining this. Now, a finite volume model can also be similar to a finite difference. I can have these square or rectangular boxes also, but typically in finite volume, I can also break it up into smaller triangles. Okay, I'll not be able to draw so many triangles. I may even break it up into these kinds of triangles and so on. Okay. Anyway, so basically, if I have a triangle, it's easier to discretize it with some kind of an irregular boundary. And these triangles need not be of the same size all the time. You can have smaller triangles, you can have bigger triangles, and so on, right? Okay, in this corner, I may need small triangles, so I may do that. Okay, whereas over here, I can use a bigger triangle. Whereas here, you see, again, I'm not saying this is necessary all the time. Even in finite difference, I can have smaller boxes, bigger boxes, and so on. But generally speaking, when I have finite difference, most of the time, all the boxes are of the same size. Okay. Anyway, in a finite volume, I can break it up into rectangular boxes also, or other shapes also. But usually in a finite element model, people will use a triangular element. So here, this is called a triangular element. Okay, it can also be a rectangular element, but generally people tend to use a triangular element in a finite volume. Oh, did I say finite volume? I'm so sorry. I'm very sorry. Finite volume is another method. Sorry, I should have said finite element. It's not finite volume, I'm sorry, it's finite element. Okay, it's finite element, and then I have these triangular elements. There's one more method called finite volume. I'm not going to discuss that now. We'll just leave it there for that. Okay, I'm sorry. Somehow I thought I had written finite element. Anyway, okay. So these are the two broad types of numerical models: finite difference and finite element. Okay, in finite difference, I have rectangular boxes that I divide up the domain into. In finite element, I can have rectangular boxes also, but usually I have triangular boxes, triangular elements. This process is also called discretization, because I'm breaking up the entire domain into these small little triangles, right? And like I said, typically in a finite element method, these triangles do not have to be of the same size. I can have small triangles, I can have big triangles, and so on. Okay. And then there are, of course, the mathematics of finite difference and finite element is completely different. They are not at all, they're not similar. I mean, apart from the difference of the shape of this, the rectangle versus the triangle, apart from that, there are other differences, but we will not get into all those details. This is not a full-fledged modeling course. We don't have the time for all of that. Okay. So just a brief background. Okay. All right. I have about 2 or 3 minutes. Let me just quickly quickly talk about the Laplace equation. So for the purposes of this introductory lecture, I'm only going to talk about the Laplace equation in 2D. Okay, so just take a look at this equation. This is my Laplace equation in 2 dimensions, dou square h by dou x square plus dou square h by dou y square equal to 0. Okay, so now my first question is, what do I need to solve this equation? If I want to solve this equation, what do I need? Anybody? Quickly. What is required to solve this particular equation? Dou square h by dou x square plus dou square h by dou y square equal to 0. It's a second order partial differential equation. It's a linear second order partial differential equation. What do I need to solve this? Because it's order 2. Yeah, Vicky, go ahead.
Boundary condition needed, sir, to solve this equation.
Very good, very good. How many boundary conditions do I need?
2.
2 in which direction?
1 in x direction and 1 in y direction.
Okay, you're 50% correct. You will need 2 in x direction and 2 in y direction. Okay. Yeah. So basically, to solve this equation, I need 2 boundary conditions in x and y each. Okay. So basically, I need at x equal to 0 and x equal to lx, let's say, and for y direction, I need at x equal to 0 and at x equal to ly. Okay. So I need these 4 boundary conditions to solve this particular problem. Okay. What does this equation represent? So this equation represents a confined aquifer at steady state. And the aquifer is homogeneous and isotropic. What else does this equation represent? There's one more. It's confined aquifer because, you know, it's dou square h by dou x square plus dou square h by dou y square. And unconfined, you have dou by dou x of h, dou h by dou x, and so on and so forth. Anyway, it's steady state because the right hand side is 0. It's homogeneous and isotropic because kx and ky or tx and ty are not there. What else is it? It is also an aquifer which has no sources or sinks, right? So this is my Laplace equation in 2 dimensions. It requires 2 boundary conditions in x and y directions each, and this is an equation which represents a confined aquifer at steady state in which the aquifer is homogeneous and isotropic and there are no sources and sinks. And now I'm going to try and solve this particular equation using a numerical approach. Okay, we will do that in tomorrow's class. So at this point, let us just stop for the day for now. Okay, so take care, everybody. We will meet tomorrow at 10 a.m. Okay, thank you very much. Take care and see you.